Hello everyone, my name's Iman. Welcome back to my YouTube channel. Today we're going to tackle a practice problem set that relates to our lecture on carboxylic acids. Let's go ahead and get started with problem number 1. Problem number 1 says, which of these compounds would be expected to decarboxylate when heated? Let's start with a little bit of review. Decarboxylation describes the complete loss of the carboxyl group from a molecule released as carbon dioxide gas. Decarboxylation is most favorable in beta keto acids and beta dicarboxylic acids, where a carbonyl group or a second carboxyl group is positioned 2 carbons away at the beta position relative to the carboxyl group. This geometry allows for the formation of a 6-membered cyclic transition state that promotes efficient decarboxylation upon heating. Let's look at our options. In option A, this molecule contains 2 carboxyl groups, but they are separated by 3 carbon atoms. So this is classified as a gamma dicarboxylic acid. And although these kinds of acids can also decarboxylate under harsher conditions, the process is significantly less favorable than in beta dicarboxylic acids. So keep that in mind as we work through each option. In B, we see a diketone. There is no carboxyl group present here, and therefore no opportunity for standard decarboxylation to occur. In C, this molecule features 2 carboxyl groups, but now they're separated by 4 carbon atoms. This makes it a delta dicarboxylic acid. And as with gamma dicarboxylic acids, decarboxylation here is possible, but unfavorable without stronger heating or catalytic conditions. Finally, in D, we see that this molecule has a carboxyl group with a carbonyl group located 2 carbons away at the beta position. This structure is a beta keto acid, which is highly prone to decarboxylation under mild heating because it can easily form the necessary cyclic transition state. Therefore, the correct answer for problem 1 is D. Problem 2 says, carboxylic acids have higher boiling points than their corresponding alcohols, primarily because blank. Here, it's important to remember that boiling points are strongly influenced by the strength of intermolecular forces. The stronger the intermolecular forces present between molecules, the more energy is required to separate them into the gas phase, and that results in a higher boiling point. Now let's read each answer choice. A says molecular weight is increased by the additional carboxyl group. Now, small changes in molecular weight alone do not account for large increases in boiling point. Intermolecular forces are far more significant than slight differences in mass when it comes to boiling behavior. So this is not the best answer. B says the pH of the compound is lower. While it is true that carboxylic acids are more acidic than alcohols, pH describes the behavior of a molecule in aqueous solution, not its boiling point in the pure phase. So this is also not the correct answer. C says acid salts are soluble in water. Again, this pertains to the molecule's behavior in aqueous solution, and it has no direct bearing on the boiling point of the neutral carboxylic acid. So, not the answer. D says hydrogen bonding is much stronger than in alcohols. This is the correct answer. Carboxylic acids, they can form stronger and more extensive hydrogen bonds because the carboxyl group contains both a highly polar oxygen-hydrogen bond and a polar carbon-oxygen double bond. In fact, 2 carboxylic acid molecules can form a stable cyclic dimer where each molecule is hydrogen bonded to the other at 2 points. And this dimerization significantly increases the strength of intermolecular interactions and consequently raises the boiling point compared to alcohols, which form only single hydrogen bonds. So that means the correct answer here is D. Let's move on to problem 3. Problem 3 says, which of the following carboxylic acids will be the most acidic? Whenever we're asked about acidity, we want to think about what stabilizes the conjugate base. In other words, after the carboxylic acid donates a proton, what makes the resulting negative charge more stable? A helpful tool to remember is ARIO. ARIO stands for atom, resonance, induction, and orbital. In this problem, all of the atoms involved are going to be oxygen. So the atom effects are not different. Resonance, that's already built into the carboxylic acid group. So that's going to be the same across the board as well. The key difference here is going to be induction. Inductive effects, they occur when electron withdrawing groups pull electron density through sigma bonds, and it stabilizes the conjugate base after deprotonation. Now, when you first look across the answer choices here, you'll notice that some molecules have chlorine atoms and some do not. Chlorine is a highly electronegative atom, and it acts as a strong electron withdrawing group. Therefore, molecules with chlorine atoms are likely to be more acidic than those without. In addition, you want to pay attention to how many chlorine atoms are present and where they're positioned relative to the carboxylic acid. Electron withdrawing groups, they stabilize the conjugate base more effectively when they're closer to the carboxyl group. Now let's go through each answer choice. For A, there is only one chlorine atom, and it is located 2 carbons away from the carboxylic acid group. This is going to provide some inductive stabilization, but note that the chlorine is not directly next to the carboxyl group. We're going to compare that to choice B. In this molecule, there are 2 chlorine atoms that are attached to the carbon directly adjacent to the carboxyl group. This is going to provide a strong inductive effect. Having 2 electron withdrawing groups so close is going to greatly stabilize the conjugate base and therefore increase the acidity. We compare that to answer choice C. There's only one chlorine atom here, and it is also on the carbon adjacent to the carboxyl group. But again, this is just one chlorine atom in comparison to choice B, where there are 2 chlorine atoms. Then finally, for choice D, this molecule has no chlorine atoms, so there are no electron withdrawing groups at all. It's going to have the least stabilization and therefore the lowest acidity. So putting all of this together, B is the correct answer. It has the greatest inductive stabilization because it has 2 chlorine atoms placed directly next to the carboxyl group. Problem 4 says, which of the following molecules could be classified as a soap? A soap is formed when a long-chain carboxylic acid reacts with a strong base like sodium hydroxide to form a carboxylate salt. This reaction is called saponification. Now, a typical soap molecule, it has 2 important parts. The first important part is a hydrophilic carboxylate head, which is water-loving. And then the second part is a hydrophobic long hydrocarbon tail, which avoids water. Because of these 2 parts, soap molecules can organize into structures called micelles in water, where they trap oils and greases on the inside of those structures. Looking at the options, for choice A, This molecule is a long-chain carboxylic acid, but it's still in its acid form. So the COOH group is still protonated. It hasn't reacted with a base to form a carboxylate salt yet. So while this could be turned into a soap, by itself, it is not yet a soap. For choice B, this is a very small molecule, only 2 carbons long. This molecule doesn't have a long enough hydrophobic tail to behave like a soap. We're looking for something with a long hydrocarbon chain. For choice C, we have a long hydrocarbon chain attached to a carboxylate anion that's paired with a sodium ion. This is exactly what we're looking for. It's a salt of a long-chain carboxylic acid, the precise structure of a soap. For choice D, this is sodium acetate. While it is a carboxylate salt, it only has 2 carbon atoms. Again, it does not have a long enough nonpolar tail to behave like a soap. So all in all, the correct answer is C. Problem 5 says, what is the final product of the following reaction? Here we're given a molecule and told that it reacts with a strong oxidizing agent. When we draw this molecule out, we notice that it is a primary alcohol. And the strong oxidizing agent that's listed here is chromium trioxide in sulfuric acid in acetone, which is known as the Jones oxidation. Strong oxidizing agents like this, they're going to fully oxidize primary alcohols into carboxylic acids. They're not going to stop at an aldehyde. In fact, they continue to oxidize all the way to a carboxyl group. With that being said, that means that the OH group at the end here, that becomes a carboxyl group, COOH. Nothing else changes in the rest of the structure. Therefore, the correct answer is going to be B. Problem 6 says, carboxylic acids can be reacted with one reagent in addition to acid to form all of the following compounds except blank. Now, we discussed how carboxylic acids are very versatile and they can react with a single reagent to form many types of derivatives. For example, reacting a carboxylic acid with an alcohol forms an ester. Reacting it with an amide forms an amide. And carboxylic acids can also be reduced to form alcohols. However, alkenes cannot be made directly from carboxylic acid in a single step. There's no straightforward one-step reaction where a carboxylic acid converts into an alkene. Producing an alkene would require multiple steps involving reduction to an alcohol first and then elimination. So the correct answer here is C. Let's move on to problem 7. Problem 7 says the reduction of a carboxylic acid using lithium aluminum hydride will yield what final product? When a carboxylic acid is treated with lithium aluminum hydride, a strong reduction occurs. Lithium aluminum hydride reduces the carboxyl group completely. So we go from this reactant, this carboxylic acid, to this final product, which is a primary alcohol, not an aldehyde, not an ester, not a ketone. So the carboxylic acid is converted into a molecule with a hydroxyl group directly bonded to a carbon that's attached to 2 hydrogens. The correct answer here is D. Problem 8 says, which of the following is true with respect to a micelle in a hydrophilic environment? A micelle forms when molecules that have both a polar head and a nonpolar tail organize themselves in a water environment. The polar heads are attracted to water, while the nonpolar tails avoid water to minimize the interaction between water and the nonpolar parts. The molecules, they arrange so that their polar heads face outward towards the water and their nonpolar tails tuck inward away from the water. Now let's go through each answer choice. A says that the interior is hydrophilic. This is incorrect. The inside of the micelle is made of nonpolar tails, which are hydrophobic, meaning they do not like water. That's why they're tucked away inward. B says that the structure as a whole is hydrophobic. This is also incorrect. The outside of the micelle is made of polar heads that interact with water, so that makes the structure on the outside hydrophilic and the structure on the inside hydrophobic. So it is not as a whole hydrophobic. C says it is composed of short chain fatty acids with polar heads. Now, this is partially true, and that's because the molecules have polar heads, but micelles typically form from long chain fatty acids, not short chains. So false statement. D says that it can dissolve nonpolar molecules deep in its core. This is correct. Because the center of the micelle is hydrophobic, it can trap and dissolve nonpolar substances, essentially protecting them from the surrounding water. So the correct answer for problem 8 is D. Problem 9 says, in the presence of an acid catalyst, the major product of butanoic acid and 1-pentanol is blank. Okay, so we're reacting butanoic acid with 1-pentanol in the presence of an acid catalyst. This should immediately tell us that we're performing an esterification reaction. And in this reaction, the hydroxyl group from the carboxylic acid and the hydrogen atom from the alcohol, they're going to combine to form water. And then a new bond forms between the carbonyl carbon of the acid and the oxygen atom of the alcohol. Now, looking at these structures, butanoic acid has 4 carbons in its chain, and 1-pentanol has 5 carbons in its chain. When we form the ester, the oxygen atom from the alcohol, it's going to remain attached to the pentyl group, while the carbonyl carbon remains part of the butanoic acid chain. So the product will be a molecule where the carbonyl carbon is connected to the butanoate portion, and the oxygen is connected to the pentyl group. This matches the name pentyl butanoate. The correct answer here is D. Moving on to problem 10. 10 says the alpha hydrogen of a carboxylic acid is blank. Let's go through each statement one by one, keeping in mind that the alpha hydrogen is the hydrogen attached to the carbon atom directly next to the carbonyl carbon. This is different from the hydroxyl hydrogen, which is the hydrogen attached to the oxygen atom in the carboxyl group. Statement 1 says the alpha hydrogen is more acidic than the hydroxyl hydrogen. This statement is false. In a carboxylic acid, the hydroxyl hydrogen, the one bonded to oxygen, is the most acidic hydrogen. It is the hydrogen that is easily lost in the typical acid-base reaction of a carboxylic acid. The alpha hydrogen, while somewhat acidic compared to other carbon-hydrogen bonds, is less acidic than the hydroxyl hydrogen. Therefore, statement 1 is incorrect. Statement 2 says the alpha hydrogen is less acidic than the hydroxyl hydrogen. This statement is true. As we just discussed, the hydroxyl hydrogen is more acidic. The alpha hydrogen, it can still be removed under certain conditions, like with a strong base, but it is not as readily lost as the hydroxyl hydrogen. So statement 2 is correct. Statement 3 says the alpha hydrogen is relatively acidic as organic compounds go. This statement is also true. Although it is not as acidic as the hydroxyl hydrogen, the alpha hydrogen is still relatively acidic, especially when we compare it to other carbon-hydrogen bonds in organic molecules. This increased acidity, it comes from the fact that the negative charge generated after deprotonation can be stabilized by resonance with the nearby carbonyl group. So once again, statement 3 is correct. So now that we've read all 3 statements, we can conclude that statements 2 and 3 are true. So the correct answer for problem 10 is D. Problem 11 says, the reaction of formic acid with sodium borohydride will yield what final product? First, it's important to know that sodium borohydride is a mild reducing agent. It is strong enough to reduce aldehydes and ketones into alcohols, but it is not strong enough to reduce carboxylic acids. Formic acid is a carboxylic acid, and because sodium borohydride is too mild, it cannot reduce formic acid. Therefore, no reaction occurs under these conditions, and the formic acid remains as it is, as a carboxylic acid. Therefore, the correct answer for problem 11 is B. Problem 12 says the intramolecular reaction of 5-aminopentanoic acid through nucleophilic acyl substitution would result in a blank. Now, we first recognize that this molecule looks like this. It has a carboxylic acid group on one end, and then 5 carbons away, there is an amino group. Intramolecular nucleophilic acyl substitution means that a nucleophile within the same molecule will attack the carbonyl carbon of the carboxylic acid, and that's going to lead to the formation of a ring. Here, the nucleophile is the amino group. Amines are good nucleophiles, and they can attack the electrophilic carbonyl carbon. Now, when an amino group attacks a carboxylic acid within the same molecule, we're going to form a cyclic amide. And a cyclic amide has a special name. It's called a lactam. So that means the correct answer for problem 12 is C. Problem 13 says butanoic anhydride can be produced by the reaction of butanoic acid with which of the following compounds? To form an anhydride, we need a reaction between 2 carboxylic acid molecules. In this case, we're going to try to form butanoic anhydride, which specifically requires 2 molecules of butanoic acid. When these 2 carboxylic acids react, they're going to first eliminate a water molecule between them, and then they will link together. This process forms the anhydride functional group. Since we're asked for butanoic anhydride, it is necessary that the starting material is butanoic acid itself. Therefore, the correct answer is A. Problem 14 says nucleophilic acyl substitution is favored by blank. Statement 1 says basic solution. A basic solution favors nucleophilic acyl substitution because strong nucleophiles like hydroxide ions are more available under basic conditions. These nucleophiles can attack the carbonyl carbon efficiently and promote substitution. So statement 1 is correct. Statement 2 says acidic solution. Even though a basic solution can favor nucleophilic substitution. An acidic solution can also promote the reaction, but through a different mechanism. In an acidic environment, the carbonyl oxygen can become protonated, making the carbonyl carbon even more electrophilic and more susceptible to nucleophilic attack. So acidic conditions can also favor nucleophilic acyl substitution. Statement 2 is also correct. Statement 3 says leaving groups that are strong bases. This is not correct. In nucleophilic acyl substitution, the leaving group needs to be a weak base, not a strong base. A weak base is more stable after leaving, so it leaves more easily. If the leaving group were a strong base, it would prefer to stay attached, and that would make substitution much harder. So putting all that together, only statements 1 and 2 are correct. So 14 is C. Moving on to our last and final problem. Problem 15 says, the reaction of ammonia with caprylic acid found in coconuts would produce a blank. First, based on its name, caprylic acid must be a carboxylic acid. And the reaction between a carboxylic acid and ammonia typically produces an amide. However, if we look at the answer choices listed, amide is not one of the options. So we need to think carefully about the type of reaction that is happening. Amide and what else is produced? Well, the production of an amide from a carboxylic acid and ammonia, it occurs through a condensation reaction. And in this type of reaction, a molecule of water is removed as a leaving group during the formation of the new bond. So caprylic acid and ammonia, it's going to produce an amide, but it'll also produce water, a water molecule. That means the correct answer for problem 15 is D. And with that, we've completed this practice problem set. Please let me know if you have any questions, comments, concerns down below. Other than that, good luck, happy studying, and have a beautiful, beautiful day, future doctors.